Kia ora koutou, everyone. Sorry I couldn't be there in person today to join you guys. As Inga pointed out, I'd like to present some of our ongoing collaborative research on trying to provide or trying to develop long-term hydroclimate or records of hydrologic change from the South Island of New Zealand. And our ultimate plan for these records is to place them in a way that we can use them to inform future planning and adaptation strategies for climate change. And you know, understanding the past is really relevant. In order to predict the planet's future, I would argue that we need to better understand its past. And you know, our instrumental record of climate change that we have derived from instrumental stations, so these are either stations on land or at sea, is really relatively short. And on the left here, I'm showing just a map of the distribution of those climate stations or those instrumental stations around the globe. And you can see that the redder dots refer to older stations or stations that have longer records. And one kind of outcome of this plot on the left-hand side is that when we look towards the Southern Hemisphere and we look in our backyard, we don't have many of those longer-term records. And so we have a very limited perspective of recent climate change. And my goal as an earth scientist is to not only look at the past, but also better understand how we can take this past information and reconcile it with the present and some of our future predictions that's predicted for the South Island. So that's really our goal. And our toolkit to do this is to look at paleoclimate records. And these can consist of a variety of different types of archives. I have a couple of examples here. You know, a key commonality between these, they all have, you know, some degree of layering or stratification. And essentially we can go back in time. And of course, these records span different timescales, but we can go back in time to get a better sense of what the pre-industrial or pre-instrumental climate was like. And the toolkit that my research group uses largely is focused on lake sediments. And so here's an example of a core down at the base of the slide. And here's some equipment we use to recover these cores in fjords and in lakes along the South Island. And these, I think, records are valuable because they provide perspective, a long-term understanding of how we can place constraints on some of these modern observations. And again, this perspective, I argue, is really important for providing or developing or informing planning and adaptation strategies for our future and our understanding of future climate change. When we compile multiple records, and as I'll do at the end of this talk, we can also get an understanding of the climate processes that are driving change in the past, and that's really valuable as well. I'm just going to give you a very brief example from a recent record. On the x-axis here, we're looking at time, and as I go forward, I'll uncover more and more of this plot. On the y-axis, we're looking at temperature change. You can see that both on the right-hand side and on the left-hand side of the panel. And what I've uncovered so far is our instrumental record and our projections for our futures based on different RCP simulations and different model runs. So here we are at present day, more or less. As we go back in time, we rely on, in this graph, we rely largely on ice cores to provide context. You can see here the axis is broken and we're looking at the last 20,000 years of Earth's history. And this asterisk points out to an interval here in the early Holocene, an interval between 9 and 11,000 years or so ago, that is just slightly warmer in the Southern Hemisphere. And although the timing is different in the Northern Hemisphere, slightly warmer than pre-industrial times. As we go farther back in time, we integrate different types of paleoclimate records, in this case, ice cores, and we can start looking at how the glacial interglacial timescales of the past, say, 500,000 years have changed. And we can use these warm interglacials as potential analogs for our future as well. Particularly, these are often used as a way to provide context for sea level rise. Going farther back in time, you can see the break-in axis again. Here we're going back millions of years. And in this case, now we need to rely on the marine record from the sediment cores collected from ocean drilling. And an interval often used as an analog is the mid-Pliocene, when CO2 concentrations were about what they are today. Temperatures were a few degrees warmer than today, as estimated. and sea level was thought to be anywhere between 10 and 20 meters higher than today. And then finally, we can go back to our hothouse world in the early Eocene, and even look at extreme events like this one at the Paleocene-Eocene thermal boundary or boundary. So these geologic records provide important context. And again, today I want to focus on our research on the early Holocene. And we have a strong interest in looking at past variations in rainfall. On the left-hand side of the plot, just looking at a map of mean annual rainfall in New Zealand. And our focus is on the southwest corner of the South Island, both in the fjords on the western margin, as well as on the eastern side in central Otago and Southland. And we'd like to provide context for these recent changes that have occurred over the last few decades. So here we're just looking at an index of summertime rainfall. Drier summers are depicted on the bottom, wetter summers are on the top. These are from 3 stations within this box on the left-hand side. And you can see there's this downward trend over the last few decades, pointing towards drier summers over this interval of time. You can also see that there's quite a bit of variability. And the driver of those changes are largely the southern hemisphere westerly winds. So these are depicted in these 2 plots on the right-hand side, where the reds and the yellows correspond to very strong westerly winds that circle the Antarctic continent. And these winds can both strengthen and intensify. The wind belt itself can contract towards the Antarctic or expand towards New Zealand. And we can also get some asymmetries in this configuration over different timescales. When we go back and look at our rainfall plot, some of the variations that we see from year to year are driven by what is called the southern annular mode. And this is a climate mode of variability that is essentially an index of the pressure gradient between the mid-latitudes and the high latitudes. And when this index is positive, we get the westerlies shifting southward away from New Zealand. This red line depicts the storm track, which is often the strongest westerly winds in the mid-level of the atmosphere. And this works to pull away rainfall from the South Island of New Zealand. And so this is an important index that dictates some of the year-to-year variations in rainfall, particularly summertime rainfall. The El Nino Southern Oscillation also plays a role. I'm not going to talk about that, but I'll come back to this index at the end of my talk. So the westerlies are really valuable. And again, our motivation is to better understand how they've driven changes in precipitation patterns over the last 12,000 years in New Zealand. And our approach, again, is using both lake sediment records from central Otago on the eastern side of the Southern Alps, and then fjord records from the western side, and looking at changes both in circulation and erosion related to rainfall. And again, for this talk, I want to focus on this early Holocene time interval, about 12,000 to 8,000 years before present. And this is one of our sites. We'll see if this plays. I hope it doesn't stutter too much. We're focusing on these closed hydraulic systems, or closed basin lakes is a better term for them, where we don't have a visible spillway for water to go. And when evaporation exceeds precipitation in these environments, the lake level drops and the shoreline progresses towards or moves towards the center of the lakes. And what we can do is we can look at ways to track the proximity of the shoreline, as you can see here in this image, towards our coring center in the center of the lake. So this is what we're going to do in this example here. And you can see these bathtub type rings along the margin of the lake that reflect past variations in lake level. So this is an example, and this is an example of a former PhD student, Greer Gilmer, finished up just recently, and she had a focus on this site and looking at past hydrologic change. We compare cores from different water depths within the lake. And so here's showing a core from 2016 in the deepest part of the lake versus a shallow core collected in 2013. This is a bathymetric map showing the how these cores are placed within the context of the bathymetry. And what we can see when we compare these cores from different areas of the lake is that some cores, the shallower cores, have these very clear, what are called unconformities or discontinuities in the sediment. Whereas the deeper cores don't have those changes in the stratigraphy. And we argue here that these discontinuities or unconformities are caused by lake level lowering and actually progressing across this coring site over here. And so our next, and this argues for a significant dry interval in the late Holocene around 3,200 years or so ago. So we can date these changes using radiocarbon and provide a time series of hydrologic change. What I'd like to do is just provide a handful of records, or compile a handful of records from the New Zealand region and the surrounds, just to see how this looks like over the last 12,000 years. So I'll walk you through this series of slides. And here on the base, we have time going from present day at 0 to 12,000 years. And these two graphs, or these two plots on these two y-axes, are temperature reconstructions from the ocean on the bottom, as well as from on land using pollen. And what you can see clearly is that the early Holocene, this interval between 11 and say 9,000 years, stands out as a warm period. We also see potentially another warm period around 3,000 years or so ago. Now, I talked to you a little bit about Lake Vaughan. We've also worked in a neighboring lake called South Mavora Lake. And here we apply a different approach because the hydrology of the lake is different, and we can actually use a organic molecule extracted from the sediment to get at some of the geochemistry of the rainfall. And this is as close as we can get to an ice core in New Zealand. It's looking at the changes in the hydrogen isotopes of rainfall over time. And in this setting, it's strongly driven by the location of the rainfall, the source of the rainfall, and temperature changes over time. We could also play some games and use some and compare and contrast some different organic molecules and get at evaporation from the same site. And that's what I'm doing here. I'm also going to add one more site, and I'll circle back. I'll explain where I'm going with this in a second here. And this is from another central Otago site from Lake Hayes, and this is in blue. And this is using a similar organic molecular approach, looking at the hydrogen isotopes of the lake water. And what I want to point out to you is that when we see these warm intervals from both warm sea surface temperatures as well as warm temperatures on land, we see indications of enhanced evaporation of lake water and potentially warmer temperatures in our lake sediment.
Chris, if you can still hear us, you've frozen on our screen.
Records from Lake. Can you hear me still?
Yeah, you just come back. We lost you for about a minute.
I'll get to my punchline here, and by adding on those discontinuities from Lake Vaughan for the Holocene, we see over the last 12,000 years, we see some evidence of significant lake lowering in Lake Vaughan and enhanced evaporation coincident with warmer temperatures from both on land and at sea as well. And so these are characterized as warm dry intervals that do not occur within our most recent records within the late Holocene. So what I'm saying is that our records that span only the last 1,000 years do not exhibit geochemical fingerprints or some of these erosive unconformities caused by low lake levels as we see in the past. And when we compare these records across the Pacific, these point towards significant weakening and contraction of the westerly wind belt away from the South Island of New Zealand. So again, these records provide some perspective on how the westerlies influence precipitation in this part of New Zealand. And so what we're trying to do now moving forward is to expand our study to different parts of the South Island using other closed basin lakes, and also focusing on trying to build a quantitative lake level curve that can essentially feed right into modern observations. And so for this, we need to do a little bit more coring and identify a few more key sites. And one of the programs that's helping us get there is the Lakes 380 program, which has a focus on the last 1,000 years, but is also working to collect cores from over 300 lakes throughout New Zealand. And so we can identify some great targets from this. So I'm going to leave it. I'll leave it there. It's at 15 minutes. Sorry, I ran a little late, and answer any questions if there's time.